So what we want to do now is we want to look at examples of reflection in plane mirrors. So a plane mirror would be a mirror that's a plane. So it's a flat, your standard flat mirror. In the next chapter, we talk about curved mirrors and how they can focus light and make images. But now we're just talking about a plane mirror. So we know that when light reflects off of a plane mirror, that the index, or rather that the incident and the reflected angles are equal to each other. So now I want to look at a little more complicated situation. So what we've got is we've got two mirrors that are at right angles to each other. So now I have a beam of light, okay, and it's going to be at an angle here that is an angle of 55 degrees from the vertical. And so what's going to happen is it's going to reflect off here, it's going to hit there, and it's going to reflect off there. So what I want to know is for the reflected beam, what angle is that compared to the incident? Well, we look at it and say, well, if this is 55 degrees right here, that means it's 35 degrees relative to the mirror. So that means this is 35 degrees right there. Well, since this is a right angle over here, some of the angles has to be 180 degrees. So that means this has to be 55 degrees right there. So that makes this 55 degrees. If I draw a perpendicular right there, that is going to be 35 degrees. So that's going to be 35 degrees. And so that means that this beam right here is 35 degrees from that. But if these two mirrors are perpendicular to each other, the perpendicular to that mirror is parallel to the other mirror. So that means that this line is parallel to that line. And so if this is 35 degrees and that's 35 degrees, that makes these two lines parallel to each other. So the incoming beam bounces back exactly parallel to the one that went in. Okay. And so this is an example of a reflector. Now this is actually an interesting thing, because what that means is that imagine radar coming in, and so if radar comes in, bounces off, it's going to go right back where it came from. So this is an interesting thing, because that means that anytime you have two perpendicular surfaces, it makes it easy for the radar to reflect back to where it came from. And that was one of the first steps in stealth technology for aircraft, because typically the way aircraft were built for since World War I, even before, is you had a lot of perpendicular surfaces on them. You had the vertical and horizontal stabilizers, you had the wings and the fuselage, they all made perpendicular angles to each other. And so what would happen is radar would come in, bounce around, and come right back where it came from. So you'd have a radar dish, it send radar out, it bounce off and come right back. And so this is how you found aircraft, radar, radio detection and ranging. And so that's the whole point of radar. And so the very first step to making aircraft stealthy was to angle all the surfaces so that they did not reflect radar back where it came from. So what would happen is you would angle the surfaces in such a way the radar would come in, bounce, and go off in some other direction. And so that would leave very little radar reflecting back to where you came from. And so that would, like I said, was the very first step in stealth technology. And so modern aircraft, modern warplanes have very few perpendicular surfaces on them if they can avoid it. Likewise, modern naval vessels have been redesigned to have very few perpendicular surfaces on them. And so everything looks very smooth rather than the chunky appearance of World War II warships. Let's do another example. Okay, so let's do one more example. Let's consider that we have here. So this, let's say this is actually tilted at an angle here that is off of the original angle. Okay, so let's say that that angle right there is going to be tilted in such a way that it's 25 degrees. Okay, so let's say this is 25 degrees away from, let's say that's 25 degrees away from vertical. It's not quite drawn right. Okay, but what you can do is you can imagine now that beam of light comes in here at an angle of 75 degrees. Okay. Well, that makes that 15 degrees. So it reflects off here. So that's 15 degrees. So this angle right here, that's 90 degrees. So 90 plus 25 is 115 degrees. So that means that this angle right there is going to be 50 degrees. Okay. So that means it reflects off at an angle of 50 degrees right there. Okay. So that means that this angle is 25, that is 50, so this angle right there is also 25 degrees. And so that means that we can now find that the angle right there between the incoming and the outgoing, okay, and so that is now going to be equal to, that's now going to be actually 175 degrees. Okay. No, it's not. No, it's not. Never mind. So that's going to be, that's going to be 65 degrees. It'll be 65 degrees. Okay. So, so there we can draw this, and this is now all geometric optics. Now, the thing about geometric optics, it actually works better if you really do draw this thing out and use a protractor and draw it out everything to the right angles. Then it's going to look right on your diagram. It's going to look like it's supposed to be. And so what you can do is you can actually sort of estimate, and you can sort of check yourself. If you get a math error that's like way off, then you can look at it and say, oh, wait, that obviously doesn't make sense. The other thing is, really, if you use a piece of graph paper and you draw everything out, and you keep the angles just right and do every step measuring the angles exactly like they're supposed to be, then the final result is going to be exactly like it's supposed to be too. So you really don't even have to do any mathematics here. You just have to know how geometry works and draw all the angles of equal incidence, equal incidence and reflection and so forth, and you can actually measure the end result without actually having to even do any math. And so this is the wonder of doing geometric optics. And so for these reflection, that's all that you need to do. In fact, there's something called ray tracing that's done in very complicated systems where the mathematics is very difficult, but you can just like draw it all out, measure things, and then the answer comes out right. And it works best if you draw it large. Full piece of paper. It works best if you actually draw it carefully using graph paper, using protractor and so forth to draw it accurately. And sometimes because you're drawing all these lines all over the place, it's helpful to use different colors to draw everything. And so that's another advantage here. And so and you can start to see why we call this geometric optics. So those are our two examples here with mirrors and reflection.